thanking the feedback by Patrice. He worked really hard, so please take your time. And the homework solutions are only a guide. They're not meant to be not meant to be complete solutions. Okay, so yeah, we can talk about more of this on Friday. Okay, fine, let's start. So last time we were going to prove proposition 4.6. It says let f be a function from S to Rn. Then the following are equivalent. F is uniformly continuous. Continuous if and only if AN, BN are equivalent, then their image is also equivalent. Equivalent just meant their limit is 0. Are also equivalent. What is it? Is it due to my teaching or fine? Yeah, if you have any comments, you can just talk to me and we can figure something out. If there's something about the course structure, we can talk. This is not set to stone. So if you're finding it too much, we can discuss. And also put your feedback on SurveyMonkey. So don't just, you can put your feedback and tell me what you think, what you need. So we'll show that A implies B. All right. Meaning we want to show, so assume F is UC. Want to show that F of AN for every epsilon positive, there exists an epsilon, so that for all n bigger than n epsilon, f of an minus f of bn is less than epsilon. Okay. Yeah, 4 math courses is too much. So let's see. So, right. Okay, so this is the epsilon. By uniform continuity, there exists a global so there exists a a global delta epsilon such that x minus y less than delta epsilon implies f of x minus f of y is less than epsilon. Okay, so but since an and bn are equivalent, for epsilon bar equal to delta epsilon, there exists an epsilon bar such that for all n bigger than an epsilon bar, an minus bn is less than epsilon bar delta epsilon. Okay, so we have to put these two together. So together, fix epsilon positive, then for all n epsilon defined as n delta epsilon, the one from here, we have that then for n bigger than an epsilon, we have an minus bn is less than delta epsilon, which gives the final result. This is what we wanted. Okay, is that okay? Yeah, too many courses. Yes. All right, now in reverse. Want to show that f is uniformly continuous. Assume, so by way of contradiction, assume f is not UC. Okay. All right, what does that mean? It means that i.e. There exists a epsilon naught, so that for any delta n, you can find two exemptions, x and yn, such that even though these are close, yet their image is not close. Is that okay? So we're negating uniform continuity. I think that is pretty clear, right? So now just take delta n equal to 1 over n, then xn, yn are equivalent. And so f of xn are also equivalent. Okay. Right. But then this gives a problem, right? So just take epsilon to be epsilon naught over 2. There exists an epsilon such that for all n bigger than an epsilon, we have f of xn, f of yn is less than epsilon. But from here, we have epsilon at lower bound, so we get the usual contradiction, 1 less than a half. Is that okay? So, okay, let's see. Yeah, let's do some examples. So this is example 4.7. Let f be e of x, 0, 1 to the reals. Okay, we'll show that it is UC. Want to show f is UC. All right. We will use the mean value theorem. By mean value theorem, what do we have? We have, okay, so yeah, we'll use the, I went too fast. So given AN, BN, equivalent sequences, want to show f of AN, f of BN are also equivalent. Is that okay? So by mean value theorem, this is equal to the derivative of f. We'll define what psi n is, times their distance, where f prime is derivative, and psi n is a mean value. So psi n is some value between the min and the max. So some guy there, and you know. Okay, so let's bring it back for the exponential. It says that E of AN, E of BN is equal to E of psi n, because the exponential is its own derivative, times AN minus BN. Okay, everything okay? Since psi n is less than 1, we get the inequality e to the 1 an bn, and then we're done. So by equivalence, of an bn, we have an bn goes to 0. Okay. So you see, this is very convenient. We didn't have to use any epsilon delta definitions. So just to reiterate, we just proved that the exponential is uniformly continuous, but this is a statement about global delta. And this proof will have been very messy if we did it with delta. So yeah, this proof will have been messy. If we work from the definition. Okay. Another remark here is that what we did is not specific to the exponential. So more generally, if f is in what is called C1, so these are functions that are continuous with continuous derivative. Then similarly, we get f of an, f of bn, equal to f of prime psi n, a and bn. But since f prime is continuous, the extreme and continuous, and 0, 1 is compact. The extreme principle gives f prime of x is less than m, gives bounded. Gives bounded. Which means that going back to this, you get m times an bn, and so again, it goes to 0. Is that okay? Does the final result evolve? Is logical end? So yeah. So what's the question? Does the final result evolve squeeze theorem? Let's see. Yes, that is exactly. So this here is squeeze theorem. Is that okay? Tongfei? Okay. All right. All right, let's see. Now, this criterion is very useful because it's if and only if. So here's another nice example that we talked about in the beginning. Let f be 1 over x, 0 to 2 to r. Want to show that f is not UC. All right. So we just have to be smart with our sequence. The sequences an 1 over n and bn 1 over 2n are equivalent. Indeed, 1 over n minus 1 over 2n goes to 0. Yet, f of 1 of, let me write this one, an minus f of bn is equal to what? Is equal to n minus 2n. So this is a way you could have reverse engineered. You could have started from here and then figure out what you needed. So this is n, and it goes to plus infinity. So f of an and f of bn are not equivalent. So f is not UC. Is that okay? I'll do one more example. It's fine. I want to really go into uniform continuity because you have many homeworks. So I want to do it carefully. All right. So let f be x squared r to r. Okay. Right. So again, take an to be n and bn to be n plus 1 over n. Okay. These are equivalent. So an minus bn is equal to 1 over n, which goes to 0. But yeah, we will show that I want to show f is not UC. Right, so yet f of an minus f of bn is equal to what? So it is n squared minus n squared minus 2, 1 over n squared. So you get 2 plus 1 over n squared, which goes to 2. So it's not 0. So f an and f of Bn are not equivalent. So f is not UC. So you see, this is very convenient. We didn't have to use any epsilon delta. So this is a very nice criterion. Okay, so let's go over some properties for the rest of the class. One nice property is what's called, it maps, this is 410. Cauchy gets mapped to Cauchy. What do we mean? If f is UC and xn is Cauchy. So let me write quickly what it was, i.e. for every epsilon positive, there exists n, so that m bigger than n implies xn minus xm is less than epsilon. Is that okay? Then f of xn is also Cauchy. Yeah, the proof is very short, so let me do it. Yeah, so for every epsilon, so want to show that, so fix epsilon, want to find n epsilon such that f of xn minus f of xm is less than epsilon. So this is a very similar argument. We did this above by no, please. Okay. By UC, there exists a global delta epsilon such that xn minus xm implies f of xn minus f of xm. So that's one fact. And then again for how is it? For epsilon bar equal to delta epsilon, there exists n delta epsilon, or n epsilon bar if you like, such that for all nm bigger than n epsilon bar, xn minus xm is less than delta epsilon. Together, for all nm bigger than n delta epsilon, f of xn minus f of xm is less than epsilon. Is that Okay. Right. Okay. Let's start with some results. Good. So another property. Okay, so this one is sort of obvious. Just to make a remark, since we work over the reals, the reals, which are complete, with the Euclidean metric, if xn is Cauchy, we talked about this, then xn is convergent. So, yeah, that's a quicker proof. So f of xn goes to f of L is also convergent. But I guess the point I want to make, but if but the above argument, but the above proof doesn't require completeness. So the above proof is true for incomplete metric spaces. We will talk about this probably in August. I'm just making a remark, nothing more. Okay, so proposition 412. Image of bounded, UC image of bounded. So let me write it differently. Bounded goes to bounded. If it's UC. Okay, so same. Let F be UC, and E inside S bounded subset. Then F of E is also bounded. So we'll prove this. Yeah. Maybe I should make a remark. Yeah, let me make a remark that this is not obvious. So, remark. If F is not UC, e.g., take f of x to be 1 over x from 0 to 2 to r, then, you know, even though 02 is bounded, f of 02 is in fact, what's the image? So it goes to infinity and it starts from a half. Is unbounded. Is that okay? All right. Okay. Proof. Yeah, so the image is like. Right. Good. So we included it in the chapter 1 notes. If if a set E is bounded, if E is bounded, then the closure meaning E bar equal to E union boundary of E is also bounded. So yeah, you can see that our C chapter, I think it's chapter 1. Maybe, no, it's topology, it's chapter 2. Okay, good. But okay, so by Hein-Borel, E bar is compact. Is that okay? Yeah, that's a good question, Austin. Yeah. So here's an example. Let me. But this is not. It's not if and only if. So on the other hand, you know, just take f equal to you know, any discontinuous function like 0, 1, then f of 0, 2 is bounded. And then let me see. But I'm wondering if here's the thing that I don't have quite ready, but it might be true. Is it true that? But can you be f continuous? Oh yeah, of course. Yeah, just take. Yeah, I mean, there's a little bit. No, like we will prove today. So today we'll prove. Today we'll prove. That compact plus continuous implies UC. Yeah, we'll come back to this discussion. Yeah, this is very interesting. Thank you. Okay, good. Right, so we have bounded and we have closed. So by closed and bounded, we get compact. How do we do this? Yeah, this proof is quite involved, so we'll do it slowly. Okay. So the strategy is, it's a very nice proof, is to extend f to the following. F bar on the closure. Such that F bar is still it's still you know, continuous, even though it might not be UC though, but we don't need it. So if, yeah, I can, then it's over. So if we can do this, if we can prove this, call it star, then what do we have? We proved it last week. E bar is compact. So F of V bar, this was the extreme principle. F E bar is compact. So that's 1. And 2, F of E, we'll show this, is inside F of bar of E bar. And so F of V is also bounded. So I hope you can follow. This is a very intricate proof. If you can find simplifications, please tell me. Yes. So let me repeat, we have to extend F to the closure, but to make sure that we still preserve continuity. That's the whole point. Then extreme principle says you have compactness, and because it's an extension, F of V is still inside F of V bar. And so since, yeah, this is the same as F of V bar is closed and bounded. So that means this guy is bounded. And so this guy is bounded. This is a tricky proof. I hope you can follow. All right. So what do we do? Building F bar. Okay. Take, so remember, E bar is E union boundary of E. Inside E, so for X in E, we define F bar of X to just be F of X. So it's an extension. So we have to figure out what to do on the boundary. So we fix X not on the boundary. On the boundary. So since this is on the boundary, there's a sequence of balls, right? And so there's a sequence of, there exists Xn inside E, such that Xn minus X naught, goes to 0. Okay, so far? Can I finish this? I'll try to finish it. Then we'll take a break. All right. Very nice. Yeah, it's a very interesting proof. So now, okay, good. Yes. Now, since xn is convergent, this will use all the machinery we built so far, almost everything. Xn is Cauchy. So we talked about this. See, I think it's chapter 2. Then from above, from UC, we have f of xn is also Cauchy. Right? So from xn we get is also Cauchy. All right. So now here's the beautiful thing, but Rn is complete. So how do you say it? The limit L equal to f of xn is a real number. It exists. Right? So this is our extension. So now we define f of x bar to be f of x if x is in E, and then to be the limit of xn when x is on the boundary of E. Okay. So that's what we did. We started from some set E, and we defined it internally, and then on the boundary, we consider the Cauchy limits. So let me finish it, and then we'll take a break. The continuity then of f bar follows by sequential continuity. So let's do this a little bit more detailed. Indeed, so if x n x naught is in E, then use continuity of f. If xn goes to the boundary, then use definition of f bar as limit. Is that okay? So what did we do? We showed that so f of bar e, so f of bar is continuous. So f of bar e bar is compact. Also, f of bar e by extension is contained within f of bar e, which is further contained within e bar, which is bounded. Okay, so let's take a 10-minute break, and then I'll stick around to look at your questions, your comments. So we'll start like 12, 11, 12, 13. A small break, but I'm here. Any comments, any questions? Hey, doctor. What? For the remark, could I check if that is generally true for any non-uniformly continuous function? Oh, no, that was a previous. Could we do bi-weekly assignment? No. I mean, I don't know. Like, I think it's very reasonable. You have a week and we put like 2-3 questions. I mean, it used to be, I used to have them bi-weekly, but people still did them the day before. So I don't think it really matters. If you work on it a little bit every day, you can get through it. But people who try to do it last 2 days, then yeah, it's too much. Also, more people should come to office hours. Only 5, maybe 4 people showed up. So, we can give you more help. It was very quiet. We finished office hour within like half an hour because nobody had questions. So, we're here to help. Could I check if the exam has been finalized? The exam format has been finalized. I mean, if you go to the syllabus, we say that, there's 10 questions. 1 question is definitions, and then, 8 questions will be like serious modifications of practice problems and homeworks and tutorials. Oh, I see. Yeah, it will most likely be time restricted. Since we only have the definition of limit at some points, would you like giving a limit of f when x of f when x goes to infinity? It's the same. Let me see. That's a good question. So let me see if it doesn't. So what's the question? The question is, what is limit as x goes to infinity of f of x? Have we not? I guess, yeah, we haven't defined this. Have we? I see, yeah. So I should go write it, yes. So suppose this is L. What does that mean? It means for every epsilon, there exists m bigger than 0 such that if x is bigger than m, then f of x minus L is less than epsilon. Is that okay? Where is it? Yeah, is that okay? So I have another 4. Yeah, I mean, look, like, I don't know what to tell you. 4, 5 courses is, I think, a bit too much for the summer, because they squeeze them, they're trying to squeeze a full semester course in fewer months. So it's a lot. You should not take too many courses in the summer, because they tend to put too much material in few weeks. As in, will we have the whole thing? No, so probably not. For the last proof, why? Will we have the whole day for the exam? Yeah, no, that's not. Why do we know there exists xn in E such that? Right. Yes. So yeah, we talked about this from chapter 2. So let's see what are we. Yeah. This is very easy. So by definition of being a boundary, there exists a sequence of balls. BRN centered at x0 that go to it. If you like, take 1 over n x0, and then you just pick one guy, one representative. So xn, xn plus 1, xn plus 2. So see chapter 2. Sangu, is that okay? Okay. Is it necessarily a limit point? Necessarily a limit point. Yeah, because we take the balls to 1 over n goes to 0. So xn minus x0 is less than 1 over n. It goes to 0. By definition of, yes, they are. So what is a limit point? Limit point definition is limit point of E. So limit point x naught. It's so annoying. Of x naught means there exists xn in E, so that xn minus x naught goes to 0. Okay. But you should have compact domain, so does x go to infinity? Yeah, so what's a good example? Let me see. How about we take something like, let's see, something simple. I mean, you could take the constant function, but I want something nicer. I know, take arctan. That's a nice example. So take arctan of x. Arctan of x goes to 1. Thing is 1. Maybe it's pi over 2. I don't remember. Yeah, I think it's pi over 2. Don't quite remember. Okay, it's pi over 2. Okay, yes, that's why. No, 1 over x is not continuous. So no, we're talking about continuity here. And then x goes to infinity. Okay. So anything else? All right. That's 0. No, I mean, I guess, yeah, sure. Yeah, we could do that. Yeah. So let me just to be more, yeah, we can take something like this. And then, yeah, you start from 1 and you go to 0. So L is 0 and L is pi over 2. Yeah, exactly. Yeah. All right. Okay. So now we do Hein-Cantor. That's a very nice one. So it says that suppose K in Rn is compact, and F is just continuous, not UC, continuous. Then F is in fact uniformly continuous. Let's see. Yeah, as a remark, going back to what we talked with Austin, so if you don't have compact, so let's go through the assumptions. If K is not compact, take F to be 1 over X over 0, 2 R. This is not compact, not closed. If, let's see, if F is not continuous, I think same example, just take same guy, but closed 0, 2. So this guy is compact, but let me see, make it, okay, let me write it more carefully. So take F of X to be 1 over X, and then just make it, I don't know, 0. Yeah, something like that. Then this is not UC, is not UC from example. Okay. Is that okay? Okay, so yeah, again, one more involved proof. So I want to say what the strategy is though. Yeah, so we want to show UC, F is UC. What does that mean? It means that fix epsilon positive want to find delta epsilon global such that if you have x minus y less than delta epsilon, you get f of x minus f of y less than epsilon. Okay. Yeah, as usual, we'll do it by contradiction. For every delta n, there exist exemptions. So that's that. Even though they're close, yet their image is not close. There's a little buffer for some. All right. The strategy is to use compactness of K on X and Yn. To get a contradiction. Okay. Everything's hard. I give up. All right. Fine. So, since K is compact, there exist subsequential limits so X and K goes to L1 and X of what do I call it? NK goes to L2. So by sequential continuity, f of x and k goes to f of L1. And f of y mk goes to f of L2 in that k. Okay. What is it? Yeah, in the midterm too. Right. Okay, fine. So claim L1 is L2. We do the usual. We'll use an epsilon over 3 argument. So this is L1 minus xnk plus xnk minus ynk plus ynk minus L2. Okay, so we want to control each of them. So first guy, we have x and k goes to L1. So take, N1 large enough such that x and k minus L1 is less than epsilon over 2 for all nk bigger than N1. Same, L2, N2, 3. Yeah. For all nk bigger than N2. And finally, take N3 so that delta of N3 is less than epsilon over 3. So this is the same delta from, let me call it star. So this delta here. So all this together gives us epsilon over 3 plus epsilon over 3 plus epsilon over 3 for n k mk bigger than the max n1, n2, n3. So that says that L1, so then take epsilon to 0, you get L1 is L2. Okay. What did we do? Yeah, we're trying to get a contradiction. So we proved that f of L1 is f of L2. That will give the contradiction. Let's see how. So remember, we have epsilon naught is less than, f of, how do you say it? Xn minus f of yn, right? That was the assumption. But then just take n, to be bigger than, how do you say it? Okay, let me do this carefully. So again, do triangle. Xn minus L1 f of L1, f of L1 minus f of L2 plus f of L2 minus f of yn. This one is 0 from above, so you just have to estimate this guys. And then I think it's clear, take n to be a subsequence. So So, you know, take, let me change the notation a little bit to make it clear. So call this K. And then take, you know, for one guy, take it to be NK. How do you say this? Yeah, so take subsequence NK and MK as above. So it's a little bit subtle, but by reordering, by relabeling, we can take NK to be MK. This is a little bit subtle point, so I'll leave it to you to think about it, and then if not, we'll talk about it. So anyhow, so again, these two are controlled by UC, by uniform, by sequential continuity. By sequential continuity, we take NK to be bigger than N epsilon naught over 2. You know, yeah, so for one guy, and then MK N epsilon or naught over 2 for the second guy, and then we just take their max. If you like. So that will give you I should probably write this as over 4. Any questions? Is that okay? All right. Sure. Okay. I hope anybody's there. Anyways, let's keep going. So yeah, this is quite an amazing result. So what it says is, if you have a compact set, it's not necessarily 1D, it can be any dimension, compact, and F is continuous. Then, you know, the image is very nicely behaved. Actually, I should draw it 1D because there's some nice pictures. So, you know, if you have compact and F is continuous, then in fact, you have UC. What does that mean? It means that any, if you pick any epsilon ball, let me say it differently. If you pick any delta ball, for some fixed epsilon. So fixed epsilon. Yeah, you can always sort of contain the graph within this epsilon ball. So as a dramatic example, let's see 1 over x, which fails. You know, if there is no small balls can get mapped to big balls. So in a way, heuristically, f being UC maps small balls to small balls. Anyways, all right, fine. Moving on. So we're gonna go into norms. So we'll define it and do some examples. And that will be it for today. So definition of norms. Yeah, we have 3 properties. So start from a vector space. Over R, the reals. Then the norm is a function on V mapping into the positive reals. With the following properties. Okay, let's see. So one guy is positive definite. So that means that if the norm is 0, if and only if x is in fact the 0 element, you have homogeneity. So take any real number. So for any A in R, X in V, you have A times V is equal to absolute value of A times, I meant to write X, X. Yeah, we'll do plenty of examples. Finally, you have triangle. Inequality. So x plus y is less than x plus y. Okay. So these are the 3 properties. So quiet. No questions. Nothing. So let's do some examples. Okay, very famous example is, of course, the Euclidean norm. So that was the square root of the absolute value squared. So let's go through the properties. Is A. So 1, if this guy is 0, want to show x is 0. Let's see. So this is the same as asking that this guy is 0, but sum of positive numbers is 0 if and only if each one is 0. So xi 0 for all I, 1 to n. And so x is just the 0 element. Okay. Is there anything special? Right. Well, I mean, you know, in let me see. I guess a good picture, a good picture to have in mind is just, you know, the Euclidean. So you have a vector x, and you have a vector y, and then what's their sum? Their sum is let me do it carefully. And this is their sum. So yeah, it says that this length plus this length will equal this length. Yeah, I'm not sure. Let me think about this. If there's anything interesting. That's a good question. So I want to think about it. Okay. Right. So then homogeneity, that's obvious. It just comes out. And then, by definition, when you square root, well, let me write it. So you have this, and so you get this. Okay. And finally, triangle. So x plus y. So I'll leave this to you. This is not too hard. So here takes a little bit of work, but work with show that, how do you say it? think. Actually, no, this one you will do it, you will do this in your homework. This is in homework. So, for general power. Okay, another very nice norm is, of course, the integral norm. Consider f. So when we write this, we mean f is on 0, 1 to r, and f is continuous. Okay, so that's the notation of continuous functions on 0, 1. Then equip this vector space. I'll leave this to you why this is a vector space. Like, why is it closed under addition? And sum of continuous is continuous, you know, with the norm which is called L1 norm, Lebesgue. That's what the L stands for. And is this the integral of f from 0 to 1? Okay. So we will work with this a lot, this norm. It will show up many times. So let's prove its properties. Let me first do the last two, because the first one is hard. So 2, and I will do the one at the end. So we want to show that, what is it? A of f is equal to A of f. I think that's clear. So let's see. VA just comes outside because it doesn't depend on x. So that's fine. 3 is also pretty easy. What is it? F plus g is equal to f of x plus g of x. Then use a triangle inequality for absolute value. And then use linearity. So I think it's clear. Actually, let me do it. Like that. Linearity of integral. Yeah, that's L1. Yes. Okay, then let's do the. This is a bit tougher. So we want to show that if this guy is 0, then I mean both ways, but one direction is easy. Then f is identically 0. So this is a nice proof. So yeah, if f is 0, then immediately you get f is 0. That's not hard. Okay. All right. So by way of contradiction, assume that f of x naught. So, sorry, let me write that there exists x naught in 0, 1, such that f of x naught, absolute value, is bigger than 0. Okay? So, yeah, in fact, we can put a little error here. Yeah. Okay. Without loss of generality, just take f of x naught bigger than epsilon naught. Otherwise, we can just take minus of it and work with that. Okay. Now, we'll get a contradiction. So let's see. Since f is continuous, take fix epsilon equal to epsilon naught over 2, then there exists, how do you say it? There exists delta epsilon such that x minus x naught less than delta epsilon implies f of x minus f of x naught is less than epsilon, which is epsilon over 2. But what does that say? It says that if you look at around x naught and you look at the ball, x naught minus delta epsilon, x naught plus delta epsilon, it says that f of x is bigger than f of x naught minus epsilon naught over 2, which by assumption is epsilon naught. So this is also positive. So it says that I can draw a line of epsilon over 2, and the graph of f will be above it, at least in this ball. So let me not draw it like this. So here, and then maybe it goes down, maybe it goes up, but at least here, it will be above this line. Is that okay? So now we're almost there. So clearly there's a problem. This is the integral over the entire of f over entire 0, 1. But then we integrate over the smaller interval, x naught minus delta epsilon and x naught plus delta epsilon. And here we showed we have a lower bound. So now this guy doesn't depend on x. So we get this times delta epsilon, which is strictly positive. So we get that 0 is above a strictly positive number. Hence, f of x is 0 for all x in 0, 1. Okay. All right. So, no questions? Okay. Another norm that we will use very heavily is the what's called the soup norm. Again, let the vector space be 0, 1. Then f of L infinity or infinity, either way is fine, is defined as the supremum over x in 0, 1 of the absolute value of f of x. So pictorially, if this is f, then there's one guy, and then you could have another guy. So this is f, and this is the soup. So this is the soup of f of x. No, we talked about this. So it was right here. Where is it? We defined it over here. All right, so yeah, these two norms, L1 and supernorm, will be really heavily used in this course. Hopefully, yeah, these are the main ones that we'll use. But yeah, let me introduce another one that you might see. Consider the space well, let me run right. So CK 0, 1. Okay, what are these guys? So this is again 0, 1. And so yeah, this guy is continuous. F prime is continuous. And so on. F of k derivative is continuous. So the first k derivatives are continuous. Equip the space with the following norm. Oh, but wait, no, I'm sorry, I went too fast. I should prove that this is a norm. Yes, of course. So yeah, let me finish the D and then I have to come back and do C. Yeah, I'm sorry. So, so equip the space with the following norm. So f of k, how do you say it? Yeah, it's fine. Yeah, let me write it as ck like this. So that's one way you can see it. This is the summation from m to 1 to k of the supernorm of the mth derivative. Okay, so now let's prove that the supernorm is indeed a supernorm. is a norm on C01. Okay, let's see. So first, which one is, yeah, the first two are easy. So let's go through the first two. So AF is equal to sup x01, A or f of x, but A doesn't depend on x, so you just pull it out, nothing else. So you have homogeneity, that's over. And then triangle is also easy. Just use the usual triangle for absolute value. And then I'll leave this to you. I think it's clear. Use that, which I think you kind of did in your homework. Use that this supremum is a subadditive. In fact, in this case, it's added. In this case, it would be equality. Actually, no, it's not that clear. But okay. No, there are cases where they're not equal. Okay. Yeah, just to make it a point that you might not have equality. So let me see. Yeah, I have to think about it, but I think there might be a inequality. Is that okay? Oh, we're almost, okay, yeah, I'm almost done. So this being 0 says that supremum from 0, 1 f of x is 0, but then that says that f of x is less than 0 for all x in 0, 1. And so f of x is 0. Okay. All right, so we're done. I will type the notes for you, and I'll see you on Thursday. So I'll stick around for questions, and that's it.